All right, you asked for it. We're going to go ahead and do it. All the extra lipids, health notes in one spot for your viewing pleasure. Let's begin. So as you've probably gathered at this point, when we've talked about all the different types of lipids there are, lipids are not defined by the presence of a particular functional group. They are instead defined on the basis of physical properties. So as you've seen thus far, there is a wide variety of structures. For instance, triacylglycerols have 3 ester bonds in a very long nonpolar region, very short polar region. Steroids are probably one of the most unique structures we've seen in lipids. They have the 4 fused rings, and that's what makes it a steroid. Vitamins have a ton of different functional groups that we've covered so far. Some of them are soluble in water, some are insoluble in water. Just the differences in structures between sphingomyelins and fatty acids and waxes, they're all very different. However, they all have the presence of some nonpolar regions. All right, so we've talked about a lot of different types of lipids, and I think it's important to kind of see how did they play out? How do we organize all of these different lipids? And so as we talked about on one of the first slides, lipids are separated into categories based on whether they are hydrolyzable or they're non-hydrolyzable. So typically we're thinking about where's that ester bond that we could split apart and break into 2 smaller molecules. So waxes have an ester bond, you could break those. They are hydrolyzable, triacylglycerols and phospholipids as well, versus our non-hydrolyzable fats, which are steroids and all of your fat-soluble vitamins. So that's kind of how we start to break apart and categorize our lipids. So we've talked about this a bit when we've talked about triacylglycerols, but I think it's kind of important to bring the point home on saturation versus unsaturation for our lipids. So foods that are rich in saturated triacylglycerols, when we say saturated, we mean they have all single bonds. They're maxed out on hydrogen, so there's no double bonds. These foods are typically your fatty red meats, cheese, butter, fried foods, ice cream, all the things that we love in life and we're not supposed to have. And here are some of the properties. They have no double bonds. They are solid at room temperature. So the lack of double bonds or the presence of saturation means that you have straight chains that can pack tightly at room temperature. They're going to be solid at room temperature. These types of fats also are going to increase your blood cholesterol level, which is something that was important when we talked about our steroids podcast. We had a discussion on cholesterol, so make sure you review that as well. Foods that are rich in unsaturated triacylglycerols are all of your plant oils, so nuts, soybeans, fish. Those are all going to have the presence of at least one unsaturated fatty acid chain. So just the presence of a single double bond means that you now have an unsaturated triacylglycerol. And I did say plant oils and I forgot. Palm oil is that plant oil that is an exception to the rule. It is solid at room temperature. So the qualities that these have, the properties that they have, is that they have at least one double bond in their fatty acid chain. Because of that, they tend to be cis double bonds, so that causes this kinking in the shape. It cannot pack tightly at room temperature. So these are fats that are liquid at room temperature, and these are responsible for decreasing your blood cholesterol levels. So whenever you hear somebody say you want to diet low in saturated fats, it's because they want you to decrease your blood cholesterol and replace that with your unsaturated fats instead. We are amazing. We were able to take fats that were healthy and make them unhealthy by hydrogenating them. So we can also create trans double bonds. Now, trans double bonds are not found in nature. Nature typically gives us these cis double bonds that you saw in the above example. Why would we want a trans double bond in our food? And the answer is twofold. We would like trans fats because we can start with something that is a good fat, a plant oil, something that has a cis double bond. If we convert that to a trans double bond, that is going to give us the same shape as a saturated fatty acid. And the reason we would like that is because we want those oils to be solid at room temperature. So from a marketing standpoint, if you think about that comparison between Ruffles and Lay's, The commercial used to say something to the effect of, you know, they'd hold two types of chips in a napkin and they'd move the chips and one napkin would have oil on it and the other would not. And consumers don't like that touch, that feel of oil. And so if you were to take the plant oil that is in that chip and create trans double bonds instead, it's going to be solid at room temperature. It's not going to leave oil behind. It's not going to feel oily. The downside of that is your body treats trans fats the same as it treats your saturated fats. So it's just as unhealthy for you. It still increases blood cholesterol level. It is semi-solid at room temperature. This is what you will see some of this in peanut butters, although there is a push to decrease the amount of trans fats in foods right now. But when you think of trans fats or fats that have a trans double bond in them, align that thought with having the same properties as a saturated triacylglycerol, a saturated fat. All right, so this is what adipose cells or fat cells are going to look like in the body. And fat cells are made up of your triacylglycerols, so we've just given you a generic one with R groups on it instead of, it doesn't matter how long these R groups are. And through the process of combustion, we can break down fats like triacylglycerols and produce CO2, H2O, and an immense amount of energy per gram of fat. If you remember back to 1201, we discussed a nutritional value about this time in class last semester. And fats have the most energy per gram, getting you 9 kilocalories of energy per gram versus carbohydrates and proteins, which only give you 4 kilocalories of energy per gram. So this is not showing you the entire reaction, but keeping in mind that triacylglycerols are a certain amount of hydrogens, a certain amount of carbons, and a certain amount of oxygens. And your body is able to process through those through cellular respiration in a very, very, very controlled combustion reaction to produce energy for the body. All right, so speaking of the energy value of fats, they do have a pretty high energy value, and because of that, they can be used as fuel for vehicles. And we found out during World War II that we could use coconut oil in place of fuel when actually World War I and World War II in place of fuel when diesel supplies ran short. Coconut oil, though, by nature is a lot more viscous than your petroleum fuels. So because of that, engines had to be modified in order to use coconut oil and to run on coconut oil. And because it's more viscous in colder temperatures, it gets really viscous and more towards the solid end. So you can't use coconut oil in a car in a cold climate. And gosh, I don't know if it's still something that is on people's minds, but probably 10, 15 years ago, people were really interested in converting from gasoline to biofuels as an economic alternative to using petroleum products. And it's really attractive. You can run your car on vegetable oil, which is cheaper, but keep in mind that the products of a combustion of any lipids, as we just saw on the last page in the presence of oxygen, is always going to be CO2 and H2O. So while this may economically be a better option, it may be environmentally on the front end a better option than mining and drilling for these petroleum products, you're still producing CO2. So environmentally, you're still producing the same products as if you were burning petroleum. So there's some benefits and some consequences to that. All right, you guys asked for my jokes. Here's my joke. He's water. He's polar. He's a fatty acid. He's non-polar. They can never be together because like dissolves like. All right, so as we talked about in our saponification reaction podcast, we talked about how to make soap. And you are going to start with a triacylglycerol. This is trialene, which doesn't matter what triacylglycerol you start with. You can start with vegetable oil. You can start with, you can start with lard. You can start with anything. You can start with plant fats. You can start with animal fats. But the goal is to hydrolyze those in the presence of a strong base like sodium hydroxide or potassium hydroxide in the presence of water. And you're going to wind up with a glycerol, which you do not want. You'll have to salt that out of the solution, remove the glycerol from that. And you'll wind up with a metal salt of your 3 fatty acids. And it's that metal salt that is your soap. It has that polar head that is hydrophilic or water-loving, and it has, oops, let's start that. And it has a nonpolar tail, which is hydrophobic, and that forms a bunch of those metal carboxylate salts are going to form your micelle that is going to pull in that nonpolar grease into the center, and it'll be easily washed away. So for every single triacylglycerol that we hydrolyze, we will get 3 of those metal salts of the fatty acids with those. Take a quick second and look a little bit closer at that salt of the fatty acid. So we have a polar head, and it is important to keep in mind that that polar head is hydrophilic. And then we have a nonpolar or hydrophobic tail. And this property that you produce with base hydrolysis of your triacylglycerol is what gives us soap that makes it have its unique properties, which we're going to see on the next slide. All right, so here's that carboxylate salt that we just talked about. Typically in this visual drawing, we draw the carboxylate salt as this cartoon rendition with the green part being that polar head where that ionic bond is between the metal and the nonmetal. And then this brown part is the nonpolar tail. So in water, your micelles are going to form, and all of those polar heads are going to come together and form the outer part of the micelle, and then inside you have all your hydrophobic tails, and that's your nonpolar interior. So when this micelle comes in contact with grease or grime or dirt, which is also nonpolar, that nonpolar dirt gets pulled into the inner part of the micelle. Because this is able to interact with water, see all those little water molecules around it, it is able just to be rinsed then off the clothes. So as long as these micelles are coming in contact with the dirt and grime, they're able to pick that up and carry it away. Here's yet another artist rendition. This is a cross-section cut of a micelle. You'll notice the polar heads and the nonpolar tails, and then what? There is grease that's been pulled right into the middle of that micelle, and now it's ready to be rinsed and washed away. These are bad jokes, guys. It's a nerdy version of a bad joke.